без своїх тери там можна. Так. Курсес, мукасесес. Три сакси. Curto esse. Happy, happy. to start. 5 minutes over time. Any more students? No, this is some kind of not my students. Oh, this one is from class my students. Okay, what I have for today? Analog to digital conversion. Let's go forward through the signal processing chain and let's speak on analog to digital conversion. Continuous signal from our words real is very good, but digital part of our system, where the brain, where the logic will be, can do nothing with it. We need to convert continuous voltage, current and so on into table of samples. We need to perform digitalization. We need to measure it in multiple points. This time discretization with sampling time. We need to incorporate special device called ADC, analog to digital converter. Analog to digital converter at first glance has input voltage. At output we will get binary data. It will be, if this is sample, let's say I, this binary data will be voltage at sampling time, let's say I tau. ADC, analog to digital converter, has analog signal on output and will produce for us its digital representation. At a first look, you can think that it's a kind of digital voltmeter, automatic or right voltmeter, where in port we have voltage, at out we should get what? This voltage measured some digit representing this voltage. ADC, our microprocessor, date, somewhere should be CLK clock, setting timing frequency, start, do it. This signal here is our voltage, and each here should be start. Also RDA signal, I'm ready. Measurement completed. Here should be our voltage at time. This date. So start signal. Where sampling should occur. Ready. We get date. Then our processor inside its memory, we should have what? Table representing all these nice red samples. And this table will slide. This table represents one period or two periods, some time frame on which later operation will be performed. So table like I is sliding. It's an observation frame with the part of signal we process numerically in present time. And this frame is sliding. Okay, let's look what's here. What can we ask from this device? We can deal with some requirements. What should it be? First, we are dealing in where our business is special area, power systems. What's specific for power systems? First, signal range, especially when we speak on currents. Current is 40 time. In general, for protection device, for device of counter fault automation, if E rated is 5 amps, we need to ensure operation up to 240 times. It's an upper boundary. It's for limited time, it's for 5 seconds, but we need to do it. On the other hand, if we speak for example, for earth fault, our low boundary may be some 100 milliamps. One of the problems of power system automation is requirement of very wide operation range. Second question, precision. We cannot omit or ignore precision requirement. Problem is especially metering fault location. In metering, it's money. In case of metering, our precision top. In case of fault location, customer would like to have less than 1% from whole device. This means what? we have quite a high requirement on measurement precision. Need to understand.
I never got this. Why is the lower amperage can also be dangerous for the device?
It's not dangerous for device. It's we cannot sacrifice precision in all signal. Problem what we can have high impedance fault with quite low fault current, and we need to still be precise. Wide range of high precision. On the other hand, usually process we are dealing with are relatively slow. We can have kilohertz some point in time, not megahertz. Excluding one special case. Its special case is wave protection. Protection what or wave fault locators. Wave which I use high voltage power line. They exploit, distribute parameters of high and overhead voltage line. This device should be very fast. In general, we have quite liberal time requirements. It's good. Okay, what can be first idea? I would like to measure voltage. We always measure voltage. Currents are converted into proportional voltage. I would like to measure voltage. How can I do? Idea number one. Comparator. X, Y. What do you know about comparators? They compare Y equal, what I'm writing. If 0, if X is below E0, and 1 if X is above E0. Yes? Something familiar from your electronic course. Real comparators do have what? Hysteresis. Oh. Up. Down. Delta X or hysteresis. Why it's needed? 1. This level corresponds to E0. Why it's needed? You have electronics course in your bachelor program, yeah? And you had, it goes after operation amplifiers. Yeah? Why this is needed? To prevent jitter. If a nice signal is 0 or threshold level, if you magnify, what we will see? This will produce what? Multiple triggering. To prevent so, delta X, is implemented to ensure that when it's triggered, it will not bounce back. It's to prevent multiple triggering and noise and jitter. So, what it's equal to at first glance? GT greater. Yeah? You can E0 one comparator, two comparators, three comparators, or 1, 2, 3, 4 comparators. Here I have 4 levels. 1, 2, 3, 4. 0, 3, 4, sorry, 1. And I don't know. Oh. Voltage rise, this triggers. Voltage is 1 unit, this triggers. Voltage is 2 units, here voltage is 3 units, here voltage is 4 units.
So more modern electronics it should be.
It's a flash ADC. They are very fast. Only you need what? First, it's error check. How can we check error? If, for example, we have level of 3, but this, let's say this one triggers and these two not. What it mean? It's impossible. This means error. So error check checks what? What if we have trigger on high level comparator? All low level comparators are also triggered. If not, it's a fault. First, it's an error check. Producing error signal. If error check completed, we have result is voltage in binary system. I can mark it. It will be in binary system. Output is voltage weighted in binary system, and encoder will convert this into binary system. It's so-called flash or instant ADC. Simple array of comparators. Checking which level. In the red. Signal path signal is compared with set of voltage level. First thing, usable in our case. Nope. That's a problem. Let's try to understand one thing, it's a resolution. What's a minimum achievable step of measurements? What we will see? Let's assert. I don't know. Go forward. This is my voltage. I have one level, two level, level 3, level 4. Zero. Okay, no, you understand. These are my voltage. I will compare. Voltage goes up. How what kind of signal will I get? Zero, zero, zero. At this point, 1. At this point, switch. At this point, switch. At this point, switch. Oh. And goes down. A result with these levels will be something like this. Understand why? Because and these points are not equal. Between these points it is 1 delta x, 1 hysteresis of my comparator. But why it's in this shape? It's a representation after. Because of distance between voltage. If I have n comparators, what will be this step? Actually, this step is A0 divided by power n minus 1. Familiar formula, no? It's a resolution. If I have 2 comparators, I will have only how many levels I can have? 2 comparators. 1, 2. 0, between 0 and comparator 1, and between comparator 1 and comparator 2. Okay. This one is bit count at the output. To get the number of required, this is bit at output. Number of required comparators, this is number of required comparators. So, if I need this gap is small, if I need something about 1% in whole range, I'm in deep problem. I will need huge array of comparators. Actually, no one in this world produces flash ADC with number of comparators less than 255. Really small. because it becomes extremely expensive. This thing will not work. But in our case, but it's very fast. In general, not good for us. Okay, where to go? Come on. Where to go, where to go, where to go? Let's try from another end. Let's try from another end. Dots. What is dots? Digital to analog converter. How can I get dots? What is dot? Some kind of block. Bits. Reference attached. It receives X as numeric data and produces output is voltage being some factor raised x multiplied by E0. Programmable voltage source. That's. See. I have matrix R, double R, 4R, so on. Matrix of resistors ending 2 power minus 1 R. Or such matrix of resistor. Amplifier, this should be, yeah, this goes to the ground and switch, here, many. X0, hop, or ground. This switch is activated by lower significant bit corresponding to 1. This one 2 power n, 2 power n minus 1, 2 power n minus 2, and so on. The switches are activated by bits of the input digit. Remember what any digit can be represented as in decimal system. I don't know, 1 10 power 0, 10 power 1, hundreds is 10 power 2, and so on. Yeah? Familiar? Binary number. Less significant by 2 power 1, it's unit. 1, 2, square, it's 4, 3, it's 8, and so on. So this one, this switch is activated by less significant byte, lower byte. This one for highest. This will work. Actually, if they may be not balanced, this can be prime. In such case, output will be E0, reference voltage, multiplied by I should be from 1. No. No. Number of making a mistake. Multiple. Wait. And should be something like this, and multiplied by R3, something like this. This is nice thing, but because we need production of such weight resistor matrix can be expensive. Not everyone, not every manufacturer is happy with this. Some design prefer larger matrix, but with equal resistor. This model with weighted resistors, no, in reality, these resistors are first made. It's a kind of hybrid AC. They are made with special paste and then cooked in oven. That's nice. And then after IC is cooked, say it's completed thermal stage, special trained workers cut these resistors to make them exact, to get them inside tolerance. It's done by hand. It's very expensive work. Really, under microscope, these resistors are made in kind of multiple parallel lines, or some area, and manually by hand some of the material, this resistance material, is removed to get the right resistance. It's very expensive work with low. Okay, they produced military grade, and they were happy if finally, from 100 ACs, 2 were stamped good. From batch of 100 ACs, only 2 were accepted for usage in military applications. Okay, another version is so-called ladder, more popular. With the ladder, you have this structure. R, double R, double R, R, so on. Double R, R, ground. Reference voltage, ground, blah blah, sorry. This way back. R double R array. All this together to operation amplifier. This one lower one corresponds to one unity, or this one to n-1, and so on. Ladder structure. Ladder structure is made from uniform resistors. Ladder structure easier to manufacture. One moment, ladder structure works as inversion. Why do we talking about ducts? Why ducts? Because if we have digital to analog converter, we can create an approximation or approximative ADC. How? Let's say we have a counter. which can count from, let's say, 2 power n to power 0. Counter of n cards. Yeah. And it can accept reset signal. Let's attach it to the x of the dot. What will happen after counter, but we need to count something. X CLK. What is CLK? Clock generator. I don't know. I use tau. Okay, TC, which produces pulse. What size of stick should I use to teach you this field? Okay, how it works? I have clock at the x input of counter. I have counter. Oh, come here. What about this monster? It's not simple, it's reversible. It can both add and subtract pulses. On each pulse, its increments +1 or decrements. What will happen? Oh my god. Yeah, pulse counter. What will happen? Time, voltage. At first, here, for example, we have LST. At this moment, counter contents is 0. Yeah? What will be output of that? 0. After 1, let's say, what will happen? 1 pulse will arrive at counter. Counter will increment itself by 1, yes? And what will happen with DAC? It will increment voltage by which step? It will be E0 divided. Yeah? Next click. What will be contents of the counter? 2. This point is double. E0 by -1. And so on, and so on, and so on. In reality, it will stop at E0. Yeah? Counter will be full. If we send reset at this moment, it will again drop. So, what's this one? It's it's an approximation of generator of linear growing voltage. Yeah? Understood? It grows linear until reset is sent. let's take our unknown voltage and send it to comparator. Here, let's take our digital to analog converter voltage, send here. Counter, clock, RST signal. Here better to have pulse forming. I need to send a pulse. What will happen if I send start command? Reset will be for and counter will start card from 0. Dark O. Until this point. What happened in this point? At this point, comparator will switch from 0 to 1. Yeah? This is output from comparator. This will send first log signal. Sorry. Not this way. Not here. Not here. Not here. I need to stop clock. So signal goes here. This signal will stop clock first and will go output as RDY. Ready? This way. I don't need start is a false format. I don't need to block start signal. I need to block clock signal. Yeah, how it works. So at this point clock will be stopped, counter freezed, and when ready signal arrives, our Y can be taken as a content of the counter. Understood? How it works? Sequential approximation. Reset, voltage 0, and then voltage grows until it reaches input voltage. At this moment, red signal blocks the counter, blocks the clock from counter, counter is freezed, and ready signal is formed. On ready signal, processor reads contents of the counter, and it's our voltage measured in units of what? In units of the dark reference. We will get our voltage measured relative T value to reference voltage of duct. Nice? Here I can reach much higher resolution. Why? Because first, ducts are produced, the only precise part is array of resistors. They are cheaper, and this array can be produced. It's no limitation in technology. No, okay, I'm wrong, but there is absolutely no limitation. It's less limitation. Producing of array of resistor, this R2R ladder resistors, and one operation amplifier is much cheaper than array of resistors plus set of precise operation amplifier. So they are cheaper and they are available up to 18 bits. Ducts are cheaper. What's the problem? Timing. Much slower, because we need to take all the steps, and that's not all. One problem: delay is function of voltage. Delay is not stationary. The higher voltage, the longer time it will take to reach it. Delay is a function of voltage. One of the modern solution, is attempt to get exact voltage faster. How can it be done? Get it faster and decrease this jitter. It's not good what delay time is. Do you know this anecdote, how to catch lion in the desert from the mass point of view? Let's assume we have desert with this is ugly line inside desert. Okay. This is conceptual line. Let's assume that we have only one line in the desert. We can split desert in half. Now we have one half and one half. One half do not contain lines, one half contain line. Split it. We have one half, 1/4, 1/8, split. Finally we will get line in the box. Yeah? Bisection, division by half. Bisection works very fast. Actually, idea of bisection solution: if you have equation f from x equals to 0, and here is true solution, here is okay, what is this b? This is a. You have isolated root between a and b. Divide by half. Find part where sign of the function changes. Again, divided by half. And so on. And in very fast, it's a very fast technique. In short time you will get your root with required precision. Here, where the idea. aggression. Here we have 1/2. We have row 1, 1/2, 1/4, 1/8, 1/16, 1/32, and so on. What's the sum of this row? If you sum all members, 0 to infinity, it will be, you should know it, 1 plus 1/2 plus 1, 2. And what's interesting, any member xi is equal to sum, okay, k, the I changes from k plus 1 to infinity. Any member is equal to sum, infinite sum of the later members of this table. In our case, if we will go in sequence E0, 1/2 of E0, 1/4 E0, and so on. If you not go step by step, by small step, but start with 1/2, then 1/4, so 1, 1/2, 1/2, from and so on. In this here, because row is limited, we have limited length of this R to R ladder array. Always xk will be greater than sum I, so on, to number. Each element is greater than sum of all others. So, we need a special kind of register. It's called sequent approximation register. Special is, so first, at time 0, voltage, input voltage, is not compared to this tiny, not compared to tiny 0 divided to this tiny voltage, but to 1/2 of E0. If it's greater, it can be lower or greater, yeah? If greater than 1/2 E0, it will be compared to 1/2 plus 1/4 of E0. If less, it will be compared to 1/4 of E0. Understand how it works? If greater here, next comparison will be 1/8, 1/16, and so on. So, power 1 divided by power of 2 is added. This way it's much faster. Row 1, 2, 1, 4, and so on converges in quadratic manner. This way better. Now next moment. Next moment we don't have one voltage. We have multiple voltage and current because we have polyphase network. We can have one ADC per channel. it's expensive. Not some can allow it, high budget, but usually we are in situation where our performance in time of our ADC overshots our requirements, so we can start to save budget. How? Multiplexing. LPF. LPF. Analog pre-processing for them all. 1, 2. M. What next? In theory, I can do what? Multiplexer. What is multiplexer? Switch selector. In theory, I can send them all to multiplexer, yeah? Controlled by my CPU, and then to my nice ADC. And what happens? I will bring myself into swamp. What swamp? Time difference between measurements. Because it's for each measurement, what will happen? All measurements will be shifted. And then what happens? They will be shifted by ADC time. One. This is point. This one is the ADC time required to perform conversion. Actually, okay, it's one shift. If I care about performance, what I need? Sample and hold. I need to freeze all my voltages. Simple sample and hold, switch, capacitor and amplifier with high input resistance. Switch closed. So when not measurement, switch is closed and capacitor voltage equals to voltage of my signal. When measurement time arrives, switch disconnects and capacitor keeps this voltage. May also have some designs to have fast discharge, to prevent back discharging into voltage source. So, sample and hold. Sample and hold. Before we said sample and hold, and all voltages are freezed. At a high-end device, in low end, they compensate sample and hold with phase correction. In good devices, sample and hold freezes all voltages. Then They are taken by one with multiplexer, measured with ADC, stored in processor memory, and then what? Release signal is sent to sample and hold, and cycle begins. Because we have time shift in measurement, sample and hold. Special circuit with storage capacitor which stores voltage for what it's guarantees. How to say, uniformity or integrity of measurements. What all voltages are measured in one particular time moment. Good, but this is not enough. Our business is rough. Usually, even precision pricing analog to digital converters are not good enough for fault protection. Usually we take high resolution ICs, but they don't have range. If we are looking for high range, they have lower resolution. In our case, in our business, typical design of sample and hold, and here I have multiplexer, selectable switch, not works. Not enough. That's why in our designs, often where I draw a nice white bullet, special circuit known as PGA is inserted. It's programmable gain amplifier. Yes, programmable gain amplifier. What is PGA? In simple case, it's an op-amp with set of resistors. With this one, gain will be 1/4, 1/16, for example. Programmable gain amplifier or range extender. Is kind of scalar. How it works? First, measurement is taken with 1/16. First, it's a rough estimation, and then second measurement with closest gain to maximum use range of ADC is taken. PGA is controlled by processor. You see what happens? How it works? First, time to do sample. Command number 1, send freeze to sample and hold. Command number 2, select channel 1 from multiplexer. Command number 3, set PGA to 1/16. Command number 4, perform measurement with ADC, rough. Establish best gain, send gain command, perform precise measurement. Set gain to 1/16, switch multiplexer to channel 1, perform the same for channel 1, and so on. And all this these devices do it inside timing of 1 millisecond. Next sample should be taken in frame 1 millisecond. All the circuits because specific of our signal. Wide range and high requirements on resolution. Sometimes, because development of chassis of protective device and development of algorithms can be done in different departments, some manufacturers prefer to order configurable chassis. So device usable, they have set of low speed channels and set of high speed channels. Low speed channels are multiplexed with multiplexer and own for all low speed memory one signal processor, one digital signal DSP, digital signal processor. For high speed channels are not multiplexed, they have one ADC, one LPF, one ADC, one DSP per channel. So they have all this track for one voltage. Such channels are costly. That's why they can have something like 9 slow and 3 fast. And you pay, fast channels add from 3 to 6,000. Not Mongolian degrees, to price of your device. They are used for fault location. These are usually they are fault location channel. Special case wave protections. Super fast ADC. What can be done? Because wave spectrum is limited, they can have one thing. They can have spectrum transfer part in their analog processing. Heterodyne. If you're interested, you can search my YouTube channel, find a lecture from course Theory of Signal. It's called Spectrum Transfer. Can watch this video. Some devices perform spectrum transfer to low frequency and process at low frequency. Okay. Sampling is not. Oh. One more special thing. All this beauty requires, if you really want to operate all this beauty, it also requires it sets high levels on its power supply. You to all this scaling machinery work, you need good, pure analog power supply voltage plus bipolar 12 or 15 volts. Some designers do what they do isolated ground for this part to prevent infiltration of power supply pulses, power supply noises into this analog part, they they isolate, even ground part is not connected directly. ISO designs with resistors with coil between grounds and fully isolated, like a hot islands. Yeah. One more moment. Hot islands. What is hot island? Hot island. Idea. You things done, for example, value. Matter somewhere here. Yeah. Here. Pure metals. See, current sensor. Its processing part. You see, they even cut. Here is no, there is no harmonic insulation between ADC and voltage. This part is under 230 volts. I call this design hot island because this part is hot. It's under line voltage. If you perform procession of hot island, your analog part is at net voltage and your ADC will be at net voltage. Output, there are two approaches. One is to isolate at the moment, you know that one of the tricks you can use isolating amplifier as PGA. But it's not a good solution. Because isolating amplifiers use modulation, demodulation, what you will get? You will get transients on every gain change. It's not a good solution. Really, one moment no one thinks about. When you change gain of PGA, the same when you switch multiplexer. It's a small transient. It can have character of decaying oscillation. This oscillation may infiltrate in your good signal. That's why if you have multiplexing design, sometimes it's preferable to have or one additional LPF before ADC or LPF, numeric LPF in digital signal processing part. So here in good style procession hot island, one ADC per channel. Hot islands are expensive if you need true precision. It may. Okay, what I see next meeting coming. Maybe some questions. No. Online, maybe online some. No question from online. So